Okay, done. All right. We're going to continue to our chapter 1. So that's the very last part for our chapter 1. Okay. Okay. Maybe before we go to that last part for our chapter 1, so let's have a very quick revision on what we have discussed in our chapter 1 here. All right. First of all, so in chapter 1, so these are the things that you need to know. Okay. So in chapter 1, okay, first of all, so make sure you are able to, let's say, given f. Okay, given as f. So maybe I would say given a subclass f, so which is a subset of omega. So then make sure you are able to verify whether f is a sigma field or not. Okay, so given a subclass F, so make sure you should be able to verify whether F is a sigma field or not. So this is the first thing that you need to do. If yes, Y. If no, Y. Yeah. And number 2, and next, so given F, given P. So then make sure you are able to verify whether P is a probability measure or not. Okay, of course, to be precise, on omega or not. So yeah, and on top of that, so then you can see you are able to derive, okay, certain simple properties of F and P. Okay, so these 3 things, and also then, so this actually should be the beginning. So that means it's like a given and a sample space. Okay, given a sample space omega. So actually it's not given, so we should say this is actually always we can construct, which is constructed, from the random experiment. Okay, so actually we can induce this from our random experiment. So once we have a given random a sample space, okay, so then make sure you can how should I say, construct or what? Okay, maybe assign. Okay, assign or construct is either one. Good. Okay, what was that? Good. F and P. Okay, a suitable one. So these are the things that we that you hopefully we expect you guys are able to achieve it. Okay, so let's go to all these things one by one. Okay, so first of all, so this will be just a very quick revision on. I think it will be better I write it out here. So first you need to look at the definition 1.1.1. Okay, and supposing this, we have a power set of omega. Okay, so let's say F is a subclass of this, so which means the elements of F is subset of omega. So then we see that this F is a sigma field. Okay, maybe we can put it in this way. Okay, maybe we can put it this way. Okay, so supposing we have a given sample space. Okay, we may put it in this way. given a sample space. Okay, so we have an object F. So we said that this F is a sigma field on omega. Okay, so here's the definition. So omega, sample space omega. Provided it fulfill all these criteria. Okay, we put 0. 0. That means, first of all, this one must be a subclass of P omega. So which is actually here. Okay, in the first place, elements of F must be a subset of omega. Okay, so that's the meaning of it. Huh? So this one just simply means its elements must be much subset of omega. So this is of the first criterion. Okay, then you come to our standard one. Next, omega must be one of the elements inside our F. Okay, and blah blah blah. Then we can come to our the second one, number 2. Number 2. So then, if A is an event, then its complement must be an event. Okay, and number 3. So supposing we have a sequence of events, so A1 up A1, A2, and so on, then the countable union of all this must be an event. Okay, so once our F fulfill these 3, in fact, past the 0, this 4, then it is so-called sigma field. Okay, so if I give you something, so you just need to verify 1, 0, 1, 2, 3 if it fulfill all these criterion, so which will be a sigma field on omega. Yeah, so that is our definitions for it. So this is how we need to do for it. So for the next one, so this will be the definitions for our probability measure. So definitions 1.1.2. Okay, again, first of all, P must be a functions on F. Okay, maybe I put it this way. First of all, 0. Okay, P must be defined on something here. So here must be something we associate an element. We associate an event. Okay, so it have to be event. We associate an event to a number. Maybe I shall put it this way. Okay, maybe I put it this way. P will associate one event to a number. Okay, a number. And secondly, so P of omega must be equals to 1. And number 2, secondly, for any event A, so the probability must be always greater than 0. So I prefer putting it this way. So that means the probability cannot be negative numbers. Okay, number 3. So again, if we consider a sequence A1, A2, A3, a sequence of events, okay, and which are destroyed. Okay, so this is very important. We only consider a destroyed event, okay, which are destroyed. Okay, so when A1, A2, A3 events, so which are destroyed, then we have the probability of the union of all, or the combination of all these events must be equals to the summation of all of them, P of it. So one is fulfill this 1, 2, 3, then we say if P fulfill this 0 to 3, okay, I include this. So then we say P is the probability measure. Okay, to be more precise on our omega. So we have these two other main definitions for it. Okay, so next we have to see how to construct the probability space based on the nature of our sample space omega. Okay, so this one okay, maybe I will combine the first two cases into one formulations. Okay, so this one. So then we have two types of it. So first, our omega, it could be discrete, okay, or the non-discrete, uncountable one. Okay, so for discrete case, so A, this is supposed to be A and B, discrete omega. So this one you refer to sections 1.1.1 to 1.1.2. Okay, so what is the formulation? So that is actually over here. Okay, so for this case, first of all, so let's say our omega is a discrete one. So that means it's we can list out all the possible. Okay, so here because I have included both cases inside, so I assume ... So it might be up to infinity, it might stop somewhere. Okay, so first omega this. Okay, next in this case, then this is quite straightforward. We can just simply take our our sigma field to be the power set. So for discrete case, that is very easy. We can just take this to be a power set. Okay. And once we have chosen this, okay, next we have step 2. Okay. A. So what we can do is, first of all, we construct our P of omega must be fulfill these two hypotheses. We summating all the K, so running from 1. So this is 1. So you have to fulfill these two conditions. So then once we have verified this, then what we can do is we can define P of A to be, we take all the omega in A and P of omega. This is the way. So the most important one will be these two. So make sure you verify it satisfies this. So if these two are satisfied, so this must be a probability measure. Okay. So what are the important thing is? Okay. So need to verify do A. Okay, these two. This is for our first case over here. So this is actually I have combined these two cases, this one together with this one. Okay, so I put it together. All right, so this is for the discrete case. So discrete case is very straightforward. So what we need to do is we can actually always pick our sigma field to be a power set. So easy. Okay. Okay, next we come to the next case. So for B, what happened if we have omega is an uncountable? So for this uncountable case, so usually we're going to take omega to be R, or omega is a sub-interval of R. Okay, usually we take this. So in this case, then we have the best options. So what we need to do is we just take F to be this BR. So what is this BR? We have discussed this today. So this is so-called the Borel sigma field. Okay, this is so-called the Borel sigma field. Okay, this is what we so-called a Borel sigma field. Okay, so which is here. Where is it? Yeah, which is here. Okay, what is this Borel sigma field? So this Borel sigma field, okay, is a sigma field generated by this class C, which is the class of all the open closed interval AB in R. Okay. All right, so forget about all this, just put it in this way. So what is this Borel sigma field? So in this case, then you may always assume that an event is always okay, maybe I put it this way. See all kind of unions. Unions. Maybe I should say countable to be more precise. Okay. Countable union and intersections of interval are events. So you may put it in this way. In fact, you may assume everything are event. So that is, you just look at, it can always be expressed as union and intersection of some kind of interval. Okay, that means you just take any interval, okay, and then you take union or intersection. So the output will be an event. Okay, so that is at least you have some idea how the event looks like. Okay, so this is the sigma field that we're going to use. Okay. Okay, so this is a property, as I say, or any interval is a Borel subset. A Borel subset is actually an event. So you may put it in this way. In this case, event means Borel subset. Okay, I hate this. Okay, so this is the case, right? So we have actually verified this. We begin with this open close interval, and after that I have verified all kind of the interval actually a Borel subset. Yeah, so this all kind of interval are Borel subset. Yeah. Okay, so this okay. Next, what we can do, we can just look at here. Usually, we can consider this case. Okay, for the next case. So next, so this is for most of the cases. Okay. So for most of cases are actually for you guys, you may assume this is all the cases, yeah, because there are some exceptional cases, so which are very rare. So you wouldn't look at that. So that's why in future you may assume all that. So for most of cases, you may follow this way to construct the probability. Okay. So what you can do is, so you look at this A. First of all, you must have a function f must be greater than 0. Okay, and later on, then you have to ensure when you do the integrations for f, so which give you value 1. So this and this. So when you have a function which fulfill these two conditions, okay, then the next thing is what we can do is we construct this P in this way, P of AB So which is just we do the integration for this function from A to B. So in this case, this P must be a probability measure on R. So again, what are the important notes? That is, so you have to make sure you need to verify 2A. That's the only thing that you need to do. Okay? You have to ensure this chosen function f will be positive, non-negative, and if you integrate this function over R, so you get value 1. Okay, so we have gone through several examples already. So these are the very basic thing that we have discussed here regarding to this chapter 1. All right. Okay, next we proceed to the last part. Okay, that is we look at some of the properties for this sigma field or the probability measure. Okay, so which is in the form of theorems like that. Okay, so theorem 1.4.1. So this is first one. It said that supposing omega f is a measurable space, so we just simply mean f is a sigma field, omega is a sample space. So then empty set belongs to here, and if an belongs to here for all n, then the intersection for it belongs to here. Well, exercise, is this a tutorial question? Yes. Okay, so this is a tutorial questions. Okay, so maybe I leave it to you. Okay, you can go and look at it. Maybe I can just look at the number 1. Okay, so this is actually the tutorial questions. Okay, so we just look at this one. Right. So theorem 1.4.1 part 1. So we just look at the proof for it. Okay, so in order to prove this, we want to prove that empty set must be an event. Okay, so to prove this, we have to go back to the idea. So I think it's better look at this one because the definition is on top there. So what is it? So you can see we have this. If A is an event, AC must be an event. Okay, this is the first thing. Next, omega is an event. Right? So we can make use of these two. So what we can do is, first we can see omega is equals to the complement of, empty set is the complement of, how should I say it? Okay, maybe I shall put it this way. Okay, I think, okay. So first, omega can be written as the complement of, empty set is the complement of omega. Okay. And also, omega belongs to F. So you can see, so that means you just replace this to be A. Okay. So using these two, then you can see omega must be an event in here. So this is by definitions 1.1.1, 1 and 2. So this is the proof of, I think maybe I will just say over here. Proof of 1. Okay. So how about the proof of 2? So this is actually, I leave it to you. So I'm not going to do it over here. So what you can do is you can use definition 1.1.1, the second one. And after that, you may, how should I say, apply the De Morgan law. Okay, using this definition 1.1.1 part 2 and the De Morgan's law, you should be able to verify this. Okay, Okay, so this is how we get the first one. And next, theorem 1.4.2. So this is so-called Moivre inequality. Let omega fp be a probability space. If A1, A2 up to AN are events, then P of A1, A2 up to N less over P1, A, and so on. Okay, here we didn't require them to be disjoint, not necessarily disjoint. Sorry, I'm running out of space, so forget it. Okay, not necessarily disjoint. So we can look at the proof for it. Okay, the proof for this is quite troublesome. Okay, so which we just need to use the mathematical induction. So you may refer back to what you have learned in calculus. Okay, so I believe. Okay, so this is the one. So let's look at the proof of 1.4.2. Okay, so we're going to prove this by induction. Okay, so first of all, we verify this for n equals to 2. So for n equals to 2, okay, you want to verify this equation. Okay, maybe we write this statement out. So this is a statement. If A1, A2 up to AN are events, then P of A1 or A2 okay, so let's say this is formula 1. Okay, all right, so the process for mathematical induction is first step. So we want to prove for the case n is equal to 2. Okay. Okay, when n equal to 2, so you can see this one I'm not going to write down. So you may refer to tutorial. So by tutorial 1, question 9. Okay, so you can see P of A1 or A2 is equal to P of A1 plus P of A2 minus P of A1 and A2. So you please verify this in tutorial 1. Okay, so however, I believe you should have seen this before. Okay, and now because of this fella is positive, okay, and we minus a positive number, then this one must be always greater or equals to P of A1 plus P of A2. Okay, so now we have verified this formula for n equals to 2. Yes, then we have verified this. So we can say that hence this formula is true for n equals to 2. Okay, next, the ideal way. So we assume.
Is it not the other way around?
Sorry?
Shouldn't PA1 and PA plus PA2 be larger than PA1 union A2?
Which one?
The third line from the bottom.
Okay, yes, right, correct. Sorry. Yeah. Okay, so yeah, thank you. Yeah, because of these numbers minus a positive number, yeah, for sure, yes, right. So it should be less or equals to this. Yeah, okay, thank you. So we got this one. Okay, now we assume this one is true for n equals to k. Okay, so that's the way. So if we assume this is n equals to k, so that means we have P of A1 union A2 up to AK less or equals to P of A1 plus P of A2 AK. Okay, we have this. Okay, then we want to use this to verify this is true for n equals to k plus 1. So we want to prove for, maybe we say we verify for n and k plus 1. Okay. Okay, so we look at it. So first of all, we take A1, A2. Okay, since we want to do it up to k plus 1, right? So that means up to AK and AK plus 1 are events. All right. Then we might need to move back to here. Again, you look at here. So if an event for all n, then the union of them must be an event. Yeah. So now we just focus on here. Okay, or maybe up to you. Maybe you may focus to here. I think I think this part. We focus on here. Do we need to do this? Yeah. Focus on here. Okay, then we're using the definitions, part 3, 1.1.1, part 3. And all these are events. Then we can see that A1 or A2 up to AK must be an event. Right? It's an event. So that means now what we can do is we can assume this is our B. So this is our A. Okay, and then you can apply the formula in tutorial 1, question 9. Okay? So then in this case, then we have, so we can say it P A1 up to AK and AK plus 1. Okay, first we have verified this already. So this is true for n equals 2. So this can be written as P of A or B. Okay, we have assumed this is B, this is A. This whole thing will be A. Okay, so then this is less or equals to P of A plus P of B. So we have actually verified this in part 1. Yeah, we have verified this in part 1. Okay, now we put it back. So then this thing, I think maybe, okay, I can put here less than PA plus PB. Now we can substitute all the things back inside. So this is A1 union up to AK plus P of AK plus 1. Okay, now in our assumptions, part 2, so we assume this is less than this. Okay, so then we can apply it. Then we can have this is less or equal to P of. Okay, so this is by part 2. Okay, now this part, you can see this less or equals to this. So which just means that this formula is true for n equals to k plus 1. Okay, so then we can say hence the formula 1 is valid for n equals to k plus 1. Okay, by going through this 3 process, 1, 2, 3, then we can have a final conclusion. Then you can say hence this formula 1 is true for all integer. Okay, so that is the methods of what we so-called mathematical inductions. Okay. Right, so this is actually something that you should have seen in your calculus course, huh? All right. So this is this theorem just to demonstrate idea how to prove this. Okay, next, this is a very important one. Okay, theorem 1.3.4. So please remember these two formula. So we're going to use these two formula quite frequent in the following chapter. Okay. Right. So one by one. First of all, if Cn is an increasing sequence, then limit of PCN will be this. When we have an increasing sequence, we can directly use this formula to calculate P of union Cn. Likewise, when this is decreasing, so you can see the only thing is this is union, this is intersections. Okay. All right. So I just verify part A. So part B, I give you here. What you can do is you can consider AK to be BK complement and then apply A. Of course, you might need to use apply part A. Of course, you need to use the De Morgan law. Okay, using part A and De Morgan's law, then you should be able to do this thing. So we just look at the proof for our part A. Right, so let's look at our setting. First of all, Cn is an increasing sequence, so that means getting larger and larger. So we want to verify this. Limit for this is equals to this. Don't mess up. Okay, so let's look at the procedure here. So take A1 to be C1, A2 to be C2 minus C1. That means a C2 intersect with C1 complement, A3 with C3 minus C2. That means C2 intersect with complement of C2. And again, please remember, C is an increasing sequence of events. Okay. If we construct our A1, A2, A3, A4 like that, so we can see that AK must be even. I think this part should be okay, right? So I don't think I need to explain this part for you because of C2 event, intersection event. Okay, so this is actually we need to use what you call it a tutorial question. Okay, and next, AK are destroyed. Okay, why AK are destroyed? So I think this is quite okay. We can look at it. This one. So just look at the picture. So just briefly give you the idea how we're going to do these things. Okay, so first of all, this is an increasing sequence. And so on. Okay, so that means it's getting larger and larger and larger, right? Okay, let's say, okay, so let's say, this picture. So let's say this is our C1. Okay. And C1 subset to C2, right? So which means C2 must be something like this, right? Must include all the C2, C1. Yeah, so this is our C2, right? And C2 is included inside C3. So that means C3 must be easy shape. Okay, so this is our C3. I don't have space. Okay, maybe put it in the center here. Let me see how. Okay, so let's say this is our C1. Okay, last one. I think 4 is good enough already. Well, I'm running out of space. Okay, so then you get all these things, right? So I think this is our C1. Next, this is our C2, and C2 is inside C3. C3 is inside C4. Okay, so this is the picture we can have. All right. Okay, so just imagine we have a picture of that. So what is our A1? So A1 is C1, so you can see then our A1 will be same. So then this is our A1. In fact, all of them. So this is your A1, right? A1 is just our C1. So A2 is C2, but excluding C1. So then what color is that? This one? I think so. Okay. So what is our A2? A2 is C2, but excluding C1. So you look at it. So which means your A2 will be the triangle, right? But excluding the one in the center. Am I right? Okay, now you look at here. I think it's clear, right? This is actually the one inside here. Okay, so that means you can see A1, A2 disjoint, right? You can get it. So you can see, you can easily get so A1, A2 disjoint. Okay, you can see. Okay, next, what is our C3? C3 is A3 is C2, but excluding C2. So that means this is the one, but excluding the triangle. So now we can see this is our A3 will be the square or the rectangle, but excluding the triangle. Only this one. Right, I think it's clear, right? So A2 is this, A1. So that means now you can easily see this, right? A1, A2, A3, these three further are disjoint. Well, I'm running out of space. I think it's good enough, right? I don't think I need to explain what is A4. So A4, I think you can imagine that will be this pentagon, but excluding the square inside, right? Okay, so this is how we construct all these A1, A2, A3, A4, and so on. Okay, so if you look at the picture, so that will be like this. Huh? So that's graphically, that will be like this. So using this process, I think by looking at this A1, A2, A3 is good enough. You can see A1, they are all disjoint. All right, these are all disjoint. So all these are events. So you might need to use tutorial questions. Okay, is it tutorial questions? No, not tutorial question actually. Yeah, you need to use theorem 1.4.1 here. Okay, if AN are events, so the intersection of them must be event 2. Okay, so that's why we can have this. Okay, all right, so one by one. Huh? So then we have this observation here. Number one, we can see this. I think first observation is straightforward, so we can see this. all the AK are events. Okay, so this is straightforward. So this is, we can directly by the previous theorems. Yeah, 1.4.1. So we got it right. So theorem. Okay, next, I think number 2, you can see that A1. I mean, maybe I just say. So all the AK are destroyed. Okay, by looking at the perf graphical description, I think we can convince that. Okay, so and number 3 is agree. So C1 is equals to A1. So C2 is A1 combined with A2. So you agree with this? So go back to our graph picture here. So you can see if we combining A1, A2, we get back to our triangle. So that is our C2, right? So if we combining A2, A1, A2, and A3, which fill up the whole rectangle here. So which is actually our C3, right? So I think we can easily get this conclusion, and C3 will be equals to A1, A2, and A3, and so on. Okay, so now what we got? We have constructed something that are destroyed. Okay, and also we have something that is a union stuff, right? Okay, now we go back to our properties here, definitions. Okay, so if AK are destroyed, then we have this. Okay, so this is our definition 1.1.2 part 3. Yeah? Okay, so we can go back to our calculations. So once we have these properties, then we can see, we can work out our calculation. So P of C is just equal to P of union of infinity, K equals to 1. So our setting here. So which is equals to P of summating. So as I said, so this is by using definitions. 1.1.23. Okay, so we can get this. And I think the next thing will be straightforward. So then this is written as limit n to infinity. So summating case from 1 to n of P of AK, right? And again, we just focus on this part only. Huh? Forget about the limit, just look at this part only. So we can apply our definition once again. Yeah. So this one, we using definitions 1.1.23 again, just for this part. Then it becomes P of here, right? But we have shown this. Okay, yeah. If we taking the union for all the AK from 1 to n, that is actually end up to be our Cn. So then we have this will be equals to Cn. Okay, so I think That is the proof for this theorem, part A for this theorem. So for part B, you need not go through all these constructions. So what you need to do is you can directly apply this formula. Yeah. So what you need to do is you just need to consider AK to be the complement of BK, and then applying the result, the formula in part A. You might need to do some derivation using the De Morgan's law. Okay. I think together with this De Morgan's law, I think not enough. You might need this. Okay, maybe I'll put it over here. Okay, so for part B, so what you need to do is you consider, this is just a hint, okay, not the proof. Okay, so let you work it out on yourself. Okay, what you can do is you may consider AK to be the complement of BK. Okay, why you want to do this? Because of, you can see BK is decreasing. So if you AK to be a complement, so AK will be increasing. So you may apply it over here. Yeah. So you consider this, then you apply part A for these theorems, as well as you might need to use the De Morgan's law. I'm not sure do you need to use this? Okay, I'm not sure. Possible. As well as, yeah, I think for sure you need this. Yeah, for sure you need this. What is this? So this is one standard formula. So P of A plus P of complement is equals to 1. So I believe you guys should be familiar with this formula. Okay, using this construction of your AK, applying part A, De Morgan's law, and together with this formula, you should be able to get a formula in part B. Okay, so I leave it to you. Okay. All right, so let's come to this one. So we can apply this formula to induce a conclusion here. Okay, this is the questions. Okay, again, we consider an random experiment. So that means you just keep on tossing a coin. Yeah, you keep on tossing a coin continuously. Okay, so then ask you a question. So what is the probability of getting at least one hit? So that's the question. So we take a coin, assuming we won't do the cheating behavior. Okay, that we don't do the cheating. Okay, so a fair coin, we just do the fair environment. So we just keep on tossing a coin. Then ask a question. So what is the probability of getting at least one hit? So would it be possible if we just tossing the coins continuously, would it be possible we always get a tail? Would it be possible? Yeah, of course. This is a mind game, right? So as a matter of fact, we cannot keep on tossing a coin and non-stopping, okay? Because one day we're going to die. At one day the earth is going to explode or blah blah. Okay, is it impossible to do this thing continuously? So, however, we can imagine this. What is the probability of getting at least one hit if you keep on tossing a coin? So, by intuition, the chances must be one, right? I don't think it is impossible. We will always get hit, get a tail, right? So how to convince that this is right? So the probability is answer. We always assume answer must be equals to 1. Okay, for sure. In one day you should get a hit. The answer is 1. Why? How to convince this answer must be 1? So we can use this to do it. Okay. Okay. So that's the setting here. So you may look at a setting for it. Yeah. So what we can do is let Cn be the event that at least one hit appear in n tosses. So I don't think, okay, Cn will be the events that at least one hit appears in n tosses of coin. So I think C1 must be subset to C2, right? So because of, I think in a way, C1 is the event consists of at least one hit, okay, hit on it, right? So and C2, so it could be tail, head, tail, at least one hit, right? So head. Okay, so I think it's clear. Okay, of course we have to include the first time. Or Cn or in n tosses. Okay, sorry. Okay, forget about it. I think you guys can look at it. So if you have C1, so only one, so then you can see this must be a subset to all these things. Okay, so and the chances of getting one hit, so that will be we combine all of them. So that means it will either get happen in the first try or the second try or the third try. So C will be on it. So C will be union of all of Cn is the event that hit will appear at least once. Okay. So now we can see P of Cn with 1 minus 1 over 2n. Okay. So this is the case. You may say in this way. For example, because if you get one hit, right? So the complement of Cn will be all, okay, maybe we can put it this way. The complement of Cn is actually equals to the event. So Cn will be at least one hit, right? So the complement of Cn will be all the tail. Okay, for n times. Okay, so we always get tail for n times. So in this case, then I think it's clear that we can see that P of Cn must be equal to 1 minus P of the complement of Cn. So that's why this is 1 minus 1 over 2 power of n. Okay, so this is how we can get it. And so when we take the limit, so this will be 0, so 1. So that's why if you're using this, PC must be 1. So that means at least one hit will appear. For sure, definitely we can get one hit. This is how we get answer here. Okay, so this will be the question that we are interested in our course here. Okay. All right, so that's the end for the first chapter. So before we proceed to chapter 2, you have any questions? So far, any questions? No, huh? Okay, good. Okay, so let's carry on to chapter 2. Right, so chapter 2 will be about this thing so-called a random variable. All right, so just a rough idea. Okay, rough idea. What is a random variable? So random variable, so it's something we assign each outcome a value, a number. So that is, first of all, we have something omega. So we have all the it consists of all the outcomes. So by using a random variable, so we corresponding each elements here to a number. So that means, roughly speaking, using this random variable is a function, domain is a sample space, and the range will be in R. So this is a function. So this is the rough idea for it. Okay, why we want to have the idea of a random variable? So the reason is here. First of all, the omega, this might not be, yeah, maybe say that, this thing. So its elements might not be numbers. Okay, so and we know math is a technique using numbers. Okay, actually the formulation of mathematics is using the numbers, right? So that's why if omega, the omega is something that is not a number, so it's very hard for us to apply the theory or the formula or techniques of mathematics to solve our problem. So that's why in order to apply the technique of mathematics, so what we can do is we use a random variable. So we transform the information here, we translate the information here in the sample space into numbers. Okay, once we come to here, then we can do some working here using mathematical formula, and after that we translate back to here to get the result, to do the interpretation for it. Okay, so roughly speaking, you can put it this way: a random variable is a function with domain is a sample space, and the range is our R here. Okay, so that's why we have to talk about functions. Say before doing this, so then let's look at this. general ideas over here. Okay, so this is some idea concept in mathematics, so which we need to use it in our course over here. Okay, so let's go to here. Okay, so let's say we have two set, omega and omega 2. Phi is a mapping. Mapping is a function. Phi is a function from omega to omega 2 for any subset B in omega 2. So this phi inverse B is all the omega. So phi omega belongs to B. So this is an inverse image of B. So I believe you should have seen this kind of concept in calculus. Okay. So just give you an example to have this. So example for inverse image. Okay, just look at some simple concept for that. Okay, now let's look at the first examples, the easy one. So again, let's say our omega is 1, 2, 3, 4, 5, 6. Okay, and let's say our omega 2 is A, B, C. Okay. Okay, so let's say we have this assignment. So let's say phi of 1 is equals to A, phi of 2 is equals to B, phi of 3 is A, phi of 4 is A, then phi of 5 is C, 6 is B. So let's look at here. So let's say we look at our B is equals to A and C. So what is the inverse image? So what you need to do is here, the idea is 1, 2, 3, 4, 5, and 6. Okay, so this is our omega. Okay, forget about this one. Okay, then we have A, B, C. Okay, so first of all, 1 to A, and 3 to A, and 4 to A. Okay, so and after that, so we have in the color. So let's say 2 to B, and okay, 6 also to B, and finally 5 to C. Okay, so B is AC, so which means we only interested on this and this. So we just go back. So that means 5, 1, and no 2, 3, and 4. Okay, so I think you can easily get this thing. So that's why the answer for this case will be one, 3, 4, 5. Okay, so the simple examples. Okay, let's look at another example. Okay, now if we look at this, omega is R, omega 2 is R again. Okay, we look at these functions. Phi of x is x squared. So look at it. Case number 1. So first, when B is 4 to 9, 2. When B is, I think maybe I use another symbol. So, okay, maybe this is a B1, this is B2. So B2 is negative 10 to 9, the interval. Okay. Can you identify the pre-image for B1 and B2 under this function? Phi x is x squared. So again, this is actually a question in calculus. So let's look at the graph. It can be quite easy. So here. So this is a graph, right? Phi x is equal to x squared. So B1 is 4 to 9. Okay. This is in the range. So that means we are actually looking at the range over here. So that is, we look at 9 to 4. Okay, so we go back here, Okay, so and this is square, right? 4, and then here must be 2 and 3, as well as -2 and -3. So that's why the first question, so we got the answer, find inverse B1 will be, okay, so you can see, okay, 1, including 4, okay, excluding 9. I think I better draw it. Oh. So excluding 9, including 4. Okay, so that's why when we pull back, so that means will be 2 is included, excluding 3, including 2, excluding 3. So the answer for this case will be -3, excluding -3, -2, including, so 2 to 3. Okay, so this is the answer for the first one. So for the second case, when B2 is -10 to 9, okay, again, we can draw the picture. So again, we look at the graph here. Okay. So -10 to 9. So again, so including 9, excluding -10. So this is the case here. Okay, so the negative part, it won't affect a thing. So that means we only have this. Okay, 3 -3. So that's mean including this. Yeah. So therefore, in this case, so the answer will be, so in fact, the negative part will not contribute anything to the answer. So this will be, find inverse of B2 will be -3 to 3, including these two endpoints. Right. For further question, okay, so these are the examples. So for further example of this inverse images, so please refer back to what you have learned in your calculus course, right? Okay. Again, I believe you might have already seen this in your calculus course already. Okay. So the pre-image or the inverse image for A or B will be this. Okay. I think good news is it's sort of like it follows some very natural formulas over here. Okay, so in general, you may get things like that. Okay, you may have a formula. This. So this is the general case or up to infinity, maybe up to infinity. So A. So that is the inverse for it. So if you take union up to infinity, so you can actually use the process of mathematical induction. You can take it out. So that will be this. Likewise, we can have a similar formula for the intersection case. Okay, so I'm not going to verify this. So however, this is quite straightforward. Okay. Okay, so next, come to here. So the next definitions, we need to apply some of the techniques for this inverse image. Okay, so that's the reason why we consider definition 2.1.1 and remark 2.1.1 here. Okay, so this is so-called measurable functions. Okay. So mapping phi from this omega f to omega 2 f2. Of course, here we are talking about one sample space to another sample space. This is a sigma field for omega. This is a sigma field for omega 2. So a mapping is said to be a measurable function if it satisfies this condition. Phi inverse b belongs to f for all b belongs to f2. So if you want to use our language to describe this, it will be like this. You get the that. So and not image under. Okay, we'll get that. An inverse image of an event is an event 2. Okay. So first of all, we have event. Okay. B is an event. Okay. So you take the inverse process. Oh, okay. Not we have not enough. We have to say. An inverse image of an event is an event 2 under a measurable function. Mapping of function. First, you have an event. Then you're using a measurable function. You pull back, so you get which is also an event. So you may interpret in this way. Okay, or an easy way will be like this. We will say an event will pull back to another event by a measurable functions. So the idea is like that. First of all, from here, it's sort of like, first of all, you have an outcome in here. You push forwards to another outcome here. Okay. So push forward. And then if you pull back, so this is my phi. Okay. So however, when you come to the inverse, then you have an F2. So that means you have any events here if you're using it. So it will pull back to another events over here. So it will push all the outcome to one outcome here, but it will pull back an events over here and back to an events here. So that is how you can interpret what I mean by a measurable functions. Okay, so mathematically it will be like this. For all events B in F2, the inverse image of B will be another event in F. That is the way. Okay, so we have these theorems. First theorem is a very straightforward one. Theorem 2.1.3. We have 3 sample space, omega 1, omega 2, and omega 3 with sigma field F1, F2, F3. Okay, so let's say we have 2 measurable functions, phi and psi. So first one to here. Here maybe I'll put together this F1, and 3. Okay, so if phi or phi is measurable and psi is also measurable, then the combinations, which is from here to here, that is this one combined with this, so this is also measurable. So this is our theorems, the picture to describe our theorems. 2.1.3. Okay, let's look at the idea for the proof. So the idea of proof is not difficult. So they will be like it. If this phi is an event, so that means the inverse process will pull all the events here and back to an event here. Okay, and so on. So now we come to here. We look at this idea for it. So the idea. Forget it. So the idea of the proof, okay, or idea of the theorem is like that. So first of all, phi is measurable. What does it mean? So if this is measurable, means that you have any events over, you have any events in F2, so it will pull back to another events in F1. Yeah, so this is actually the meaning of it. So in hypothesis. On the other hand, we said that this is also measurable. Psi is another measurable functions from omega 2 to omega 3. So by our definition, which means it will look at all the event in F3 and then it will pull back to another event in F2. Okay, so now you just imagine it. So that means you take any events here and will come to an event here and it will back to another event here. So that's why it's sort of you go through this process, you will reach here. Okay, so you can stop in the middle and then you directly come to this part. So this is the idea for the proof for it. So to write down the proof, okay, so that's the way to write it down. Okay? So this like that. So given any event A in 3. Okay, if we want to show that this is an event, that means what we need to do is we have to achieve this. Given this, then we must have this. Hence, psi composite with this inverse of A belongs to here. Right? So that is the definition. If this is, you begin from here, we get this. Okay. If we begin from here, we get this. Okay, in the middle, you try to come up with your explanation why you can from this step to this step. Okay, so if you're able from this step and come to this step, okay, then by the definitions, then you can claim that. Hence, so this is by the definitions of measurable function. Why missing here? Okay, so A. Correct? Okay, so that this is the idea is like this. It's because of here, maybe I give you a picture. So the reason is now we have a omega 1 to omega 3. So after the combination, this one combined, this will be from omega 1 or F1 together with 3 here. Okay, so that's why in order to show that this function is a measurable function, you have to pull all the event here and back to an event here. So this is something that you need to show. Right? Okay, so I give you guys a think about it, how to fill in the blank. Actually, it's already here. Just forget about this, okay, this page, and you try to fill in the blank over here. Yeah, if you're able to fill in the blank, so congratulations, you already know the term, you know the rules to play the games, right? Okay, as usual, 7:30 now. Let's take a break for half an hour. After 8 o'clock, we shall continue the second section for today's lecture. All right, so see you afterwards. By the way, any questions? No, okay.